Hi, I'm Oli. I'm the builder of this robot and the creator of this video. Pause. First, let's talk about our team. We have been competing in robot competition for over 2 years, and our friendship made us work well together. Let me introduce you to our members. Our team consists of this guy.
Hello, my name is Kavan. I am team coordinator and document designer.
And this guy.
My name is Book and I'm the programmer.
After I introduce you to our team, let me tell you about our past experience together. For the past 2 years, we have been competing in robot competition together, and I think we have some experience. This is actually our second time competing in this category. We have learned our flaws from last year and hoping for a greater achievement. You may wonder why we participate in this competition. Here is the answer. We believe that this kind of things can change the future, so we want to learn more about machine vision, and this competition is the perfect opportunity for us to learn about these technologies. By joining this category, we hope to gain even more experience and hopefully some prize. Also, we want to use the certificate we got in our portfolio for application to university that specialize in this kind of technology. Before everything else, we need to come up with a plan first. By planning and scheduling our work, we can keep track of our current progress. Let me explain how we operate. This is our schedule. We have organized tasks by dividing the work among team members based on each person's specialized skills. This approach ensures efficiency and allows everyone to contribute their strength efficiently. To give you a clearer picture, here's our real-time work progress, showing each team's member working period. Book, it represents in red, Kalpan in yellow, and myself in blue. From our national round design and last year design, we learned that weight, repairability, and durability are the most important aspects a robot needs to have. This time, our robot is almost fully 3D printed, with the use of some specific Lego parts to reduce weight and add more strength. While designing, we implement a latch design that allows us to lower the number of bolts and nuts used for lighter weight, and allow us to take apart the robot for repair easily. One of my proudest design I implemented is the C-clip locking mechanism I found online, which consists of 2 parts, the rod and the clip. To lock 2 parts together, we create a hole for the rod to go through, then C-clip lock them in place. For our Lego parts, we use mainly the differential gear and axle. Lego parts are mold injected, making each part precise 2 mm and can withstand a lot of stress from the torque created by the motors.
Now let's go over the electronic parts we used. We used a large power function motor made by Legos for the motor because it has small form factors but is powerful enough for our robot and easy to connect to our chassis. For steering the robot, we used the Geek Servo 2 kg 360 degree servo instead of this, which makes the designing process a pain. This servo can withstand a lot of weight, can connect directly to the controller, and is compatible with Legos, which connect directly to our chassis. We use the Gravity URM09 ultrasonic distance sensor to detect the track wall because it gives precise distance measurement, which helps the robot avoid crashing into the wall. Previously, we used a color sensor to detect the line, but it could not tell apart the red and blue lines in the bad lighting condition. So this time, we chose the CX03 blue light sensor and the CX03 red light sensor. Why, you may ask? Because the blue sensor can detect both color lines, and the red sensor can detect only the blue line. With this, we can use it in a logic to differentiate the line's colors. We use the DY25 gyroscope to make sure of the robot orientation and allow precise turn. The reason we select this gyro sensor is because of both its compact and efficient functionality. We choose the CX Switch 01 because this is a straightforward touch sensor. We use it to start the program without touching directly with the controller board. For the main controller, we choose the Arduino Mega 2560 Release 3, which performs tasks very fast and efficiently. We changed to this board from the previous one because always capacity to support more than one UART communication, which we use for gyro and the camera. For the camera modules, we choose the OpenMV H7R1 cameras. This camera responds faster than what we used to use, and it can detect color better. It also allows us to configure and program it using the OpenMV IDE, which comes with a built-in library for easy use, so we can utilize all of its hardware in our mission effectively. For the port expansion board, we choose the Gravity I/O sensor shield and the Gravity 2x2A motor shield. They allow us to connect and use various components such as the sensors and motor of our robot. We choose an 11.1 volt 3-cell LiPo batteries as our power source because of its improved capacity that ensures stable power for a long duration from the 7.4 volt we use in the national round. We choose the HW360 version 6 step-down module to convert the 11 volt battery input to 9 volt stable output to expand the usage time and for compatibility of the motors. Lastly, we choose an SPST on-off rocker switch between the battery and the board to easily turn off the robot, and as a safety cut. Before we go over the robot design, let me tell you about the program we use for the design, which is Blender. We prefer to use Blender instead of other software because it is free and easy to use. As the designer of the robot, I already have experience using this software, so modeling the robot this time is less challenging. Why do our robot look this way? Our robot is based on our national round robot with improvements such as the hinge design and C-clip. We create a space for the battery and move the step down from the back of the robot to under the board. We added a second ultrasonic sensor in front of the robot, which we will use to aid us in the parking mission. As you can see, the camera is at the back of the robot. This is because if the camera is in front, it will pass the obstacle block before the whole robot avoids it. For the wheel, we use two Lego wheel size. The bigger one is in the back, improving the speed, while the smaller one, which is wider, is in the front, providing traction to the steering. For the handle, we increase the height by around 10 to 15 centimeters to avoid hitting and damaging the camera with our hand. Additionally, there's a hole on both sides of the handle to attach the activating switch so the user can move it according to their preferences. Now let me tell you how the program works. The first round, open round, the robot needs to complete 3 laps around the field without crashing into the wall. This code configures a robot with several motor sensors and a PID controllers for gyro-based navigation, and set up motor pins, light sensor pins, and controls for turns and line detection to guide the robot's movement. Then this setup function initializes serial communication, servo pin, and sensors. It calibrates the compass with zero yaw function, wait for the button to press, and prepare the system by attaching servo and activating the PID controllers. Finally, the loop function is where the robot's movement happens. It continuously reads sensors value, adjusts motor speed and steering using PID feedback. The robot checks the button status to start or stop and uses sensor data to correct its direction. The servo handles the steering, and when the robot reaches a certain count, it stops.
At the start of the round, the robot begins by detecting traffic signs and avoiding them. If it detects a red traffic sign, it will steer to the right. If it detects a green traffic sign, it will steer to the left. After passing through the first section of the field, the robot detects a line on the ground. If the line is red, it will subtract 90 degrees from its heading or turn right. But if the line is blue, the robot will add 90 degrees to its heading or turn left every time it sees a line. Next, the robot encounters a parking lot. To prevent collisions, it uses the same method as for avoiding the traffic sign. If the robot turns right, it will avoid the parking lot to the right. But if it turns left, it will avoid the parking lot to the left. Before completing the second lap, the robot must decide whether it needs to make a U-turn. It does this by detecting the first traffic sign behind it. This could be in the 7th or 8th section. If the robot detects a traffic sign in the 7th section, it updates the variable last block. After detecting the 8th line, it continues to monitor traffic sign. If it detects a red block, it will make a U-turn. If it detects a green block, it will continue moving. But if it detects nothing, it will refer back to the last block variable to check whether it was red or green. Once the robot completes 3 laps, it continues moving straight, then moves backward to face the direction it needs to go to find the parking lot. At this point, it follows the outer wall until it detects the parking lot. After complete 3 laps, the robot no longer needs to avoid traffic signs as per the rules. When the robot sees the parking lot, it will avoid it and move backward, positioning itself facing the parking lot. Then it will drive straight to the midpoint between 2 walls and then stop the program.
Let me tell you something. From the beginning, when we starting to practice this competition, we have faced many problems and of course we fix it along the way. Right now, everything is going according to plan and we're starting to pack up for Izmir, Turkey. We are hoping that our robot will work as well as what we practice and hope that we might get some prize. Thank you.